In this video, we are going to be doing free response question number 2 from the 1998 exam. So there's a space shuttle astronaut in circular orbit around the Earth, and he or she has an assembly consisting of 2 small dense spheres, each of mass m, whose centers are connected by a rigid rod of length L and negligible mass. The astronaut also has a device that will launch a small lump of clay of mass m at speed v0, and we want to express our answers in terms of m, v0, L, and fundamental constants. Initially, the assembly is floating freely at rest relative to the cabin, and the astronaut launches the clay lump so that it perpendicularly strikes and sticks to the midpoint of the rod, as shown. This is the diagram that they give to us, and I just want to point out that since this rod is of negligible mass, we don't have to account for the moment of inertia of the rod itself. And since it says that these spheres are dense and small, we can treat them as point particles, so we don't have to worry about the moment of inertia of a sphere either. The first part of the problem asks us to determine the total kinetic energy of the system after the collision. The fact that this diagram is given to us and the fact that the problem says collision indicates to me that this is going to be a conservation of momentum problem. Since this clay blob hits the assembly in its midpoint, that indicates to me that it will not rotate, so it will be linear momentum. So the initial momentum of the system will equal the final momentum of the system. The initial momentum of the system is just the momentum of the clay blob, so it'll be m v0. And then the final momentum of the system is this sticks to here, and they will all move that way together. So we have mv0 equals m plus 2m times vf. Simplify it a little bit. Just add the m plus 2m equals 3m. The m's will cancel out. We have v0 equals 3vf. We want to solve this expression for vf, and we get vf equals v0 over 3. Now, we want to find the final kinetic energy of the system, so we have to plug that into our formula for kinetic energy, which is just 1/2 mv squared. In this case, m is actually 3m, because it's the mass of this whole system, and vf is what we just found. So we do v0 squared, or sorry, v0 over 3 and all of that squared. So that'll be v0 squared over 9, which you see here. This will cancel out so that you end up with a 3 down there. 2 times 3 is 6. So your final answer to this part of the problem is m v0 squared over 6. The second part of part A asks us to find the change in kinetic energy, and that's pretty easy because we just want to do the final kinetic energy minus the initial kinetic energy. The initial kinetic energy is just 1/2 mvi squared. The initial kinetic energy of the system is just the kinetic energy that that clay blob had. So it's mv0 squared over 2. And then the change in kinetic energy is kf minus ki. We just solved for kf, so it's going to be m v0 squared over 6 minus m v0 squared over 2. We want to put that over the least common denominator, so for this one we multiply both the top and the bottom by 3. We want to do this subtraction, and that'll end up being negative 2 m v0 squared over 6, and that will simplify down to negative m v0 squared over 3. So this is our final answer to part 2 of part A. Now the astronaut does a slightly different experiment in part B. The experiment is repeated with the clay lump striking perpendicular to the rod, but this time it sticks to one of the spheres. So instead of striking right here, right at the original center of mass, it sticks to this sphere here. Determine the distance from the left end of the rod to the center of mass of the system immediately after the collision. We want to assume that the radii of the spheres and clay lump are much smaller than the separation of spheres. Again, we're able to assume that so that we don't have to account for the moment of inertia of the spheres themselves. We can just treat them as point particles. To find the center of mass of an object, you take each of the masses times their position, add them together, and divide it by the total mass. Since the problem asks us from the left end, we're going to call that position 0, and this here will be position L. So the center of mass is equal to this mass right here times its position, which is 0, plus these two masses times their position, which is L, divided by the total mass, m plus m plus m. So we end up with 2ml over 3m. The m's cancel, and our center of mass ends up being at 2l over 3, which is right around here. Part 2 of Part B asks us to indicate the direction of the motion of the center of mass immediately after the collision. Now at first, the center of mass will not rotate, it will just move in a straight line right after the collision. So we just need to draw an arrow that looks like that, where the center of mass just moves straight up. Part 3 of Part B asks us to determine the speed of the center of mass immediately after the collision. That is essentially asking us for the same thing as Part A, because if it's the center of mass, it's just going to move in a linear way and not rotate. So the initial linear momentum equals the final linear momentum. The initial, if you recall, is just the momentum of the clay blob, and the final is just the whole assembly moving together. The m's cancel out. We have v naught equals 3f. So Vf will be equal to V naught over 3. So that's what they're looking for Part 3 of this. Part 4 of Part B asks us to determine the angular speed of the system immediately after the collision. So as I was pointing out before, the whole system will rotate. So in this case, we need to think about conservation of angular momentum. The initial angular momentum equals the final angular momentum. Now you may think, why does it have an initial angular momentum? So an object can have an angular momentum relative to a point that's not in its path. So that's what's happening with that clay blob. The center of mass in this case is its axis of rotation. So this clay blob is originally 1/3 L away from the axis of rotation. We want to use our formula for angular momentum, that's mvr, where m is the mass of the clay blob, so that's just m. V is v naught, and the original distance from the axis of rotation is just L over 3. That's this 1/3 L right here. Then the final angular momentum, well, this whole thing will be rotating like that, and it'll be rotating around the center of mass right here. So we want to use our formula for angular momentum, that's I times omega. We need to figure out what the moment of inertia of the system will be after the clay blob strikes the sphere here. So the final moment of inertia will be this guy times its distance from the axis of rotation squared plus these two times their distance from the axis of rotation squared. That's what I have right here in this formula. And obviously we can simplify that. Oh, and this should be big M. Little typo there. So 4L squared M plus over 9 plus 2L squared M over 9. Add that all together, and we get 6L squared M over 9. Then obviously that can cancel out and reduce to 2L squared M over 3. So now we can set our initial angular momentum equal to our final angular momentum. So our initial is this, our final is this, and we want to determine the angular speed, so we want to solve for omega f. So first, I'm noticing that the m's will cancel out. One of these L's will cancel out, and both the 3's will cancel out. So we'll end up with V naught equals 2L omega F. And then we can just divide both sides by 2L to get omega F. So this is our final answer to that part of the problem. The last part of this question asks us to determine the change in kinetic energy as a result of the collision. So we want to find the final kinetic energy, and that's a little bit trickier than before because it'll have translational kinetic energy and rotational kinetic energy. The translational kinetic energy will just be how fast its center of mass is moving. So it's 1/2 mv squared, where m is the 3m, and the speed of the center of mass is this, which we found before. And then the rotational kinetic energy is, if you recall, 1/2 I omega squared. So 1/2, this is our moment of inertia, and this is our omega squared. We can simplify that. So what I did from this step to this step is I canceled some stuff here so that it became mv naught squared over 6. And then what I did here was I did v naught squared, and then 2 squared is 4, L squared is L squared. We can cancel out some stuff. So these L squareds will cancel out. And, oh, sorry, there should be a v here. So it'll be m v naught squared over 6 plus m v naught squared over 12. We can put those over the least common denominator and get 3 mv naught squared over 12. And that reduces to mv naught squared over 4. Now the change in kinetic energy is the final minus the initial. The initial kinetic energy is just the kinetic energy that the clay blob had, which would be mv v naught squared over 2. That's just 1/2 mv squared. So we end up doing the final, which is mv naught squared over 4 minus mv naught squared over 2. And our final answer is negative mv naught squared over 4. And that is that problem.